Thank you to the organisers of this meeting. So I was asked to come here by those organisers, in particular Phil Donoghue, to review what we know about this topic. In other words, to review what is known from a geochemical data point of view, as opposed to a geochemical model point of view that Tim dealt with on Monday, and perhaps Andy Ridgewell will more later. About this interesting period of time, independently of the fossil record. And in one sense, I'm a good person to do that. I have spent some time trying to understand the rate and pattern of chemical weathering on the modern Earth and on the past Earth. But in one sense, I'm not a good person to do this because my work personally has been restricted to the Cenozoic and trying to understand the interactions between mountain building and chemical weathering and CO2 drawdown in that period of time, and I've not ever personally dipped into the murky world of the Paleozoic. So in educating myself about this, I've co-opted another Phil, who has started working on the Paleozoic, and I'll show you some of his data later. But in the end, please excuse me if I say something egregiously wrong about the Paleozoic or about plants. Be gentle with me and blame Phil Donoghue instead for inviting me. So of course, one of the other things I've been doing to try and educate myself is to read papers on this period of time, and often co-authored by people in this room. And this diagram from one of those papers summarizes nicely and by way of introduction the impacts that plants might have on chemical weathering rates on the continent, and therefore what we might expect to see in records. So I kind of divide these into three. There's the fact that plants certainly accelerate the hydrological cycle, and chemical weathering of rocks of course needs water, and it needs CO2 from the atmosphere to generate acidity. I sort of would group these three, 1, 2, and 3 here, into processes that modify the chemistry of soil water. For example, plant exudates in search of nutrients affect chemical weathering reactions. Litter decay produces organic acids, and if it gets oxidized enough, CO2, and of course plants get CO2 into those soil waters as well. And then the third broad process is the fact that plants stabilize the physical environment in which chemical weathering occurs now, and perhaps has occurred in the distant past. So the models that Tim talked about on Monday sort of tried to parameterize those plant influences into forcing factors. And you see here's the forcing factors to do with chemical weathering associated with land plants. And those models then try to reproduce or to simulate really important aspects of atmospheric chemistry, such as the greenhouse gas content, for example. And this is a Bob Berner version of one of those models, where you see that atmospheric CO2 plummets upon the evolution of plants. And one question is where that might happen. Tim was suggesting it may be that this effect, at least for oxygen, might be earlier than this model would have it. And these factors that go into this model, the acceleration factors for chemical weathering, whether you have plants or whether you have bare rock, come from studies in the modern environment, places like Iceland, where you can study, or indeed experiments like Tim was talking about, where you can study the impact of plants on weathering rates. And of course, it matters to oxygen as well, although chemical weathering is not so important there. It is slightly in that oxidative weathering is a sink for oxygen, but the really important impact of plants, of course, is organic carbon burial. So the questions that Phil Donoghue kind of posed me are kind of these. What do we know independently of all this from records of, say, ocean chemistry about the pattern and rate of chemical weathering on the continents? And can those records help us understand the timing and the nature of the impact of plants on biogeochemical cycling in the Paleozoic? And for example, can they help constrain model inputs? You know, the acceleration factors, for example. I don't think they can, but or can they help validate these model outputs? And I'm afraid to say that the short answer to that is kind of not really, to be honest. But there is some potential before you all leave the room. And let me explain why that is briefly before I get into the data. I think there are two things. One is a very soluble problem at this stage, and one is less soluble. The soluble problem is that there isn't much data in the Paleozoic. So a lot of the newer tracers that we developed of chemical weathering on the continents simply haven't been applied very much to the Paleozoic. What people tend to do is work back through time, start with the easy stuff further towards the present, and then work back. But there are some new tracers that are, I think, really going to help, and I'll show you some exciting, I think, really exciting early data from the Paleozoic that's not been published yet, that comes from Phil Pogge van Strandman. So that's an optimistic scenario. Getting more data is relatively easy. But the other problem that I'm going to illustrate first, and to stay pessimistic for a while, is the fact that a lot of the tracers that we've historically used to look at chemical weathering rate on the continents are complex. Their controls are multidimensional, and therefore it's very difficult to interpret them in terms of one process, and we need multidimensional constraints to understand these multidimensional controls. And just to illustrate that, before I get on to the kind of new, more exciting data, I'm going to start with something that we've been doing, geochemists have been doing for a long time, and that is building records of the strontium isotope composition of the oceans. Now, I'll explain in a minute what strontium isotopes are and why this tells us, and it definitely does tell us something about chemical weathering. The question is what. So this is something I'm going to talk about. The both things I'm going to focus on are records of the chemistry of the ocean and how that changes, and that's important because the oceans are the bucket into which at least some of the products of chemical weathering are emptied. We can build records of ocean chemistry. This one comes from marine carbonate, which is a chemical sediment that precipitates in seawater. We can date it, and that precipitate records something about the chemistry of the ocean at that time. We have a lot of data for strontium. The line here is supposed to indicate some confidence in the data. That confidence really starts with the fact back here that we begin to have macroscopic body fossils, which have some integrity in terms of their strontium isotope composition. They don't change much during diagenesis, for example, after they're made. Back here, the data is significantly less confident because it doesn't come from those kinds of macroscopic body fossils. And there's plenty of strontium in carbonate, so it's easy to measure. Strontium is an alkaline earth like calcium, so it substitutes for calcium. And that makes it easy to measure, but it also makes these records robust against diagenesis. It's pretty hard to change the strontium isotope composition of a carbonate just because there's so much strontium in it. But what does this mean? And I'm afraid I know there are at least some people in the audience who will never, perhaps ever, have come across this before. So we are going to do just 2 minutes of Isotopes 101 and go right back to basics, but it won't take long. So here's a periodic table. Here is where strontium is. As I said, it's an alkaline earth. It sits in the same group as calcium, so it's got similar chemistry. And the reasons there are variations in the strontium isotope composition of the Earth in general is the fact that there's an isotope of rubidium-87, which decays to strontium-87. It's got a very long half-life, over 10 times the age of the Earth. But even though the decay is slow, you build up over time variations in the strontium-87 to, say, normalized to 86 ratio of Earth materials. And again, just to stay away from the oceans and weathering just for one more slide, the main reason for that, the main reason for variations in the strontium isotope composition, so the amount of this 87 isotope on Earth in different Earth materials, relates really, the big first order process is the chemical differentiation of the Earth. So that started maybe 4 billion years ago, perhaps, maybe even earlier, maybe a bit later. And if we had some notional bulk Earth evolution, that would be this black line. So this ratio goes up through time from the beginning of the Earth to now because rubidium is decaying. How fast it goes up depends on how much rubidium relative to strontium there is in the bulk Earth. And what started to happen early in Earth history is that you started melting the mantle. The melts that you produced rose to the surface, solidified eventually as continental crust. Rubidium is an element that preferentially goes into a melt relative to strontium, so the crust that you formed started to evolve faster because it had more rubidium, producing more of this, and the residual mantle left behind evolves more slowly. Younger crust formed from that mantle would go off like that as well, and recent volcanic rocks directly derived from the mantle would be here. So there are variations in the strontium isotope composition of the crust, because some of it is old, it has lots of rubidium, and it has had a lot of rubidium for a long time. Some of it is less old, some of it is recently made. So, if we go back now to the oceans and that strontium isotope record, one of the things, I can see an upcoming problem, I think, maybe. One of the things that affects the strontium isotope composition of the ocean is not chemical weathering, as we will get to in a minute, but is the leakage of hydrothermal fluids out of the oceanic crust as seawater interacts with basalt to alter it. Oh no, it is there. So if we take, for example, the Cenozoic portion of the strontium isotope curve, which has been controversial, this rise has been controversial, and what causes it? One possibility, for example, is that because the strontium that comes out of hydrothermal systems essentially comes from the mantle, it's got a strontium isotope composition that's way off down here. So one thing that could drive seawater up is simply the decreased input of that volcanic strontium through time, maybe. But the more interesting thing for us then is the opposite of that. We know that the continents are enriched in rubidium. They've been enriched in rubidium, many parts of them, for a long time. They therefore have lots of 87 strontium because that rubidium's been decaying away for a long time. And so this rise could be due to the increased input from rivers to the oceans through time via increased weathering of silicate rocks. And one of the possible interpretations of this rise since 40 million years is that it's due to the uplift of the Himalayas, and the uplift of the Himalayas might generate faster chemical weathering rates in high mountains, and because you have faster physical weathering rates, etc. But actually, I mean, the salutary point for the Paleozoic is that we don't really understand why. There is still debate about why this happened. And one of the reasons for the debate is shown on here. So this is data for the strontium isotope composition of rivers. And I just want to take this apart a little bit because it's important to understand the complexity of these controls on seawater strontium isotopes. So what it shows is the strontium isotope composition of rivers here, and then it shows the reciprocal strontium concentration here. So high strontium concentrations this end, low is this end. And what it shows is something that we are interested in, that the silicate rocks on the continents, because they have lots of rubidium and some of the continents are old, have high strontium 87-86 ratios. And this is interesting in terms of chemical weathering and atmospheric chemistry, because we can say, well, if we see more of this in the oceans, we must be weathering more of these silicates, drawing down more CO2, for example, and that would be a simple thing. The other end of this, these are rivers that drain dominantly carbonates. The carbonates are rich in strontium, so they're down this end. They don't have much rubidium. They have low rubidium strontium. And they have this kind of strontium isotope composition. They define the other end of this kind of broad trend, mostly. And so there are other kinds of strontium draining in from the continents that is nothing to do with silicate weathering. It's carbonate weathering, which of course doesn't affect atmospheric CO2. And that's a complication, but that is not so bad a complication, because you can view carbonates as one big short-term cycle, right? You precipitate them in the ocean. They have this kind of isotope composition. You uplift them onto the continents, you chemically weather, and it's just this one big thing going round and round, kind of buffering seawater to this sort of isotope composition. And then this is the thing that we're interested in: what drags seawater up in strontium isotopes, and it would be this. But the problem is, there are two problems that I want to point out. One problem is that many of the Himalayan rivers are up here, right? They are rich in strontium, and they're radiogenic. They shouldn't be like that. That's not what this trend, they fall off this trend. And one reason for that in the Himalayas, a particular reason that may be general though, is that the Himalayan rocks are in a metamorphic belt. They've been heated to very high temperatures, and during that metamorphic event, the strontium in the carbonates and the silicates has been homogenized. So these carbonates, and they are carbonate-dominated rivers, that's why they have so much strontium, have radiogenic isotope compositions because they've been mixed up with the silicates during this metamorphism. And then the other problem is that so I said that the crust, some of the crust is old and therefore has had high rubidium for a long time and therefore is radiogenic. But of course, some of the crust is new. It's just come out of the mantle. So we have continental flood basalts on the continents. The Blue Nile is a river that drains one of those continental flood basalt provinces. And of course, those rivers are draining silicate continental crust as well. And they're not up there, they're down here because they are young crust derived from the mantle recently. So this thing here, can we use this rise as indicating increased input from rivers through time via weathering of silicate rocks? Can we say that? Or could this simply be driven by changes in the isotopic composition of that flux from the continents to the ocean, because different rocks have different strontium isotope compositions? And I think most people now would say that the strontium isotope curve is kind of controlled by these big scale tectonic kind of events. The prevalence through time of continental flood basalts, the prevalence of mountain belts and the rest. And just to finish this bit about strontium, just for fun, to look at what the strontium isotope record does through the time period that you guys are interested in, well, I mean, the answer is not really very much. It's pretty, it's kind of flat. And I don't think that it's going to ever tell us in detail about the things that you might want to know at this meeting. So that's the pessimism over. I'll get a bit more optimistic now, but optimistic up to a point, because what I'm going to show you now is another way, I think a much better way of looking at chemical weathering rate and pattern on the continents. But what some of you may have realized already is that I'll tell you what this is in a minute. It's lithium isotopes, and this is a record in carbonates again. And as you can see, there's lots of data over the last 50 or 60 million years of Earth history, and this has been focused again on trying to understand what has drawn CO2 down through the Cenozoic. But the period of time that you're interested in, there aren't any data. And this is typical of these new tracers, but this is a very soluble problem, and I think I am not being too overexcited in saying that there is something pretty important going on in there somewhere, and if we had more data, we might understand it and be able to say something useful with it. Okay, so why does lithium isotopes in marine carbonate tell us about weathering? Well, again, some isotopes 101 for a couple of slides. Here's lithium. It's a low mass element. Now, lithium is a completely different type of isotope system. There are no radiogenic contributions to any of the lithium, either of the lithium isotopes. They are just there. They've always been there. Most lithium is lithium-7, 92.5%, but these are average natural abundances because there is variation in this lithium isotope composition, which we express, as many of you will be familiar with from oxygen and carbon isotopes, in terms of this delta value, which is the 7, it's heavy over light, the 7:6 ratio in a sample relative to a standard, and we talk about it in terms of parts per thousand or per mil variation. And in the environment, there is about a 30 to 40 per mil variation in lithium isotopes in different Earth materials at the surface of the Earth, or 3 or 4%. We can measure lithium to maybe 0.1 per mil, so these are big variations relative to the uncertainties. Why do lithium isotopes vary? Well, they vary for the same reason that other stable isotope systems that you might be more familiar with vary, like oxygen or carbon. They vary through two different kinds of processes. There's equilibrium partitioning of the isotopes between minerals and fluids that occurs. It's just an equilibrium thermodynamics thing. And there is an effect that you know well from photosynthesis, carbon in photosynthesis, whereby the lighter isotope has a faster reaction rate. Okay, so in understanding what that record of lithium isotopes might be telling us, I think this is a really important data set. It comes from Himalayan rivers again, and what it shows here is the lithium isotope composition of the dissolved lithium in a variety of rivers in the Himalayas, all the way across the Himalayas. Here is a hot spring, and here is the lithium isotope composition of the suspended and bed load in those rivers, and it's plotted here against lithium concentration in those rivers. Now, what we know about lithium is that the continental crust it varies a bit, but is relatively homogeneous in its lithium isotope composition. It's about the top of that red band, or the same as that hot spring. And that's a good thing because it's not like strontium. If we weather the continental crust, we know that it will have we know the average lithium isotope composition it should have. Whereas remember, strontium varies depending on what kind of rock you're weathering. The other important thing about lithium is that silicates are the dominant source of lithium to rivers. Carbonates don't have much lithium, right? So the silicates dominate. The other important thing about this slide is the first important thing about this slide is this hot spring. Now, a hot spring, when it weathers, if you like, when it dissolves a rock, it dissolves the entire thing. There's a bit of silica left, maybe, but it basically dissolves the entire thing. So this hot spring, all the lithium in the original rock that is now in solution in this hot spring water, all the lithium is there that was originally in the rock, and so the hot spring records the isotope composition of the rock, right? You just transfer the lithium from the rock into the water in the hot spring. What is clear is that these rivers don't do that. They are variably heavier, enriched in lithium-7, and they sort of follow this kind of interesting trend. And this trend is to do with the intensity of weathering. Now, what do I mean by the intensity of weathering? So in the weathering environment on the continents, what you have is, this is a schematic, you have rock uplift that's pushing stuff through this chemical weathering zone at the surface. There's the top of the chemical weathering zone with plants, here's the bottom. And the chemical weathering front gradually moves this way, and the rock is moving that way, right? And so how intensely you weather, whether you take a rock and you weather it and dissolve it up 100%, one control on that is how fast rock uplift is occurring. Because if rock uplift is occurring really fast, erosion will physically move the weathering material out of the weathering environment before weathering can occur, right? So one control on how intensely weathered stuff is before it's moved out into a particulate load is how fast rock uplift is occurring. So the other thing that affects weathering intensity, how much of the rock do you dissolve up and get into the aqueous phase relative to leaving behind in a solid phase, is to do with secondary mineral formation. So many weathering reactions do not just take a mineral in a rock, turn it all into soluble components and ship those soluble components out into river water and into the ocean. What you do often is the insoluble components are transferred not into solution like these things, but into clay minerals and iron oxide minerals. And these remain behind in the soil, and of course are a very important component of that soil. And they're really important for lithium isotopes, as it turns out, because lithium substitutes into these secondary minerals. It goes into sites, both in interlayer sites and structural sites. And the important thing about us, for us here, is that the light isotope preferentially goes into those sites. So when you have lots of secondary mineral formation, when you do not have very intense weathering, when you are not transferring a mineral completely into solution, shipping it out in solution into the ocean, when you are making lots of secondary minerals, as you always do in soils, then lithium-6 will go into those secondary minerals. And this is why we see this pattern in these Himalayan rivers. This is really intense weathering. You transfer all the lithium in the rock into the aqueous fluid. But as you go this way, we are going up the Himalayas to very high altitudes where uplift is really fast. where temperatures are low and weathering rates are low because chemical reaction rates are low. There's less water, there are less plants probably, and so that is what's determining that trend. So, and the modern world, even though the continental crust is about +3 in terms of its lithium isotope composition, the globally average discharge-weighted, lithium concentration-weighted flux to the oceans and rivers is +23. It's a long way heavier because of this non-complete weathering on the continents. Okay, so what I'm telling you is that lithium is going to tell you about the intensity of weathering in the past. Probably, because there's one more complication, and that is that, well, it's shown on this slide. So we're talking about the oceans here. What we measure is the oceans, and what we measure in the oceans today is an isotope composition of +31 today, for example. Rivers come in with +23, as I just said, and there is another source, hydrothermal fluids from ridges, just like for strontium. And one puzzle here, initially, is that if you average these sources to the oceans, you get an overall input of +15 per mil. But the oceans aren't +15 per mil, they're +31. And the reason for that is there are outputs as well. We think the oceans are broadly chemically in steady state. Stuff comes in, stuff goes out, and the oceans sort of stay the same through time. And that output is basalt alteration. Lithium is taken up during that process, and it's taken up into sediment. And these preferentially take out the light isotopes. All right? So instead of having seawater that's +15 because of these inputs, you are continually taking out preferentially the light isotopes, which pushes seawater up. So that's a complication, but it's a complication that we can probably work with and deal with. If we go back to this data again, the really remarkable thing, I think, about these data is that, as I said, this happens here. Today, we have a riverine input of 23 per mil, the dissolved input to the oceans. If these data are right down here, then what we're seeing back here is a riverine input that is not really heavy because of the lack of intense weathering, but a riverine input that is basically the same as the continental crust. And that is a fundamental change, and if this turns out to to hold, it's really, really important. But what does it mean? I don't think it means what people might want it to mean. This does not tell us anything about the rate of chemical weathering, right? It does not tell us anything about the rate of CO2 drawdown, the sort of interesting things you might want to learn. It tells us about how intense weathering was on the continents. And of course, there are things going on that are probably all related to the advent of plants on the continents, right? That almost certainly are also showing us that there's changes in the physical environment that are probably also leading to changes in the intensity of weathering. So, we know this really interesting work on fluvial style in the Paleozoic. We moved from dominantly braided rivers to meandering rivers during the Paleozoic, which means you had almost certainly more stable soils, these sort of riparian environments where you had different kinds of soils. You may even have had different kinds of clay minerals in those soils. So there's some data that's sort of scrappy, but it's kind of also intriguing. Here's our interesting period of time. Here's the lithium record with a bit more data on it now from other people. And it seems that the kind of clay that you are getting changes around this time, from a clay mineral assemblage that is mostly illite, potassium-rich clay, to a smectite, perhaps dominated clay assemblage, probably also to do with plants. So there are, right, okay, I am right there. And so to conclude, so the interpretation of radiogenic isotopes, as I've shown you, is very non-unique, and it is probably controlled by a large-scale tectonic. There is something really interesting going on with lithium at the sort of time that's interesting to you people. But what's going on is complex. There's a series of observations. Secondary mineral formation probably changed quantitatively, qualitatively, probably both. There was this stabilization of these new sedimentary environments, soils and stuff. And the relationships of all this to the rate of chemical weathering and CO2 drawdown is just not simple. And we need a multi-dimensional approach. For example, lithium isotopes, I don't think tells us anything about the amount of stuff going into the ocean. It tells us about the type of stuff, the intensity of weathering in that environment. We need a better tracer of the size of the chemical weathering fluxes. And all of this is going to have to be coupled with models such as Tim was talking about on Monday. And I know Tim and Phil have a grant proposal in to do that, so be nice to it. Okay, thank you.
Well done, Derek. Thank you.